A very good afternoon from Team Blackops. I am Balaji from National Institute of Industrial Engineering, NITIE, Mumbai from India. I would like to introduce my teammates Shivashankar, Praveen and Vimal. First of all, we would like to thank SCNext for providing us this wonderful opportunity to compete on a global platform. Next slide please. To begin with, we outline the problems faced by Sidewall Corporation, which manufactures sidewalls for aircrafts. The company is facing problems to meet the demand that inventory turns need to double without impacting its current on-time performance. In addition, the plant's efficiency and quality numbers are also going down. To help Sidewall Corporation to solve its problems, we have used the theory of constraints approach. We have identified the system's constraints and decided how to exploit them. We have subordinated everything else to exploit the constraints. We have then elevated the system's constraints, and whenever a constraint is broken, we repeat the process. By implementing the proposed solutions, Sidewall can achieve a drastic increase in its inventory turnover while improving on-time performance. In addition, the plant's efficiency and quality numbers will also improve. Next slide please. The first question we are going to address is, what is the real problem for Sidewall? We will be focusing on multiple levers while talking about problems. The primary problem of the plant is identifying its goal. The current goal of the plant is to produce as efficiently as they can, which is wrong. Most of the time, the struggle for high efficiency takes the plant in the opposite direction of making money, which should be its goal. The next lever is the mode in which the plant operates. Currently, the plant operates based on orders which are considered urgent. But we need to change the way we think about production capacity. We can't measure capacity of a resource in isolation. Its true productive capacity depends upon where it is in the plant, and trying to level capacity with demand shouldn't be done. The third lever is a basic assumption. The plant currently works on the assumption that making people work and making money are the same thing. The basic rule has been just keep everybody and everything working all the time. And when there isn't any work to do, make some. And when they can't make work, shift people around. But in order to actually make money, we should question this assumption. The next lever is how we focus when we measure results. The operations in the plant are based on local optimums instead of focusing on the plant as a whole. But we have to talk about the plant as a whole, not one department within the plant. And as already mentioned, the plant is facing problems to ship orders on time even though material is released on schedule. This is further compounded by the fact that each client considers his project to be urgent, and the plant frequently has to go into expediting mode to meet delivery schedules, which affects other orders. The final lever is the inventory strategy of the plant. The plant maintains high inventory to improve both the efficiency and utilization. However, due to demand from the corporate, the inventory turnover needs to be doubled without impacting current on-time performance. I would now like to call Shivashankar to continue.
Thank you, Balaji. The next question we are going to talk about is what new approach should Sidewall follow. First of all, Sidewall should focus on making money and stop assuming that making people work and making money are the same thing. For it to make money, it should focus on three measurements which express the goal of making money perfectly. The first one is the throughput. The second one is the inventory. And the third one is the operational expenses. Now, how do we define these? Throughput is the rate at which the sidewall generates money through sales. The next measurement, inventory, is all the money that sidewall has invested in purchasing things which it intends to sell. And the last measurement, operational expense, is all the money sidewall spends in order to turn inventory into the throughput. Therefore, our recommendation for making money is that Sidewall should increase throughput while simultaneously reducing both inventory and sales. But how do we achieve this in practice? That's where resource-based optimization comes into play. Basically, all the resources in a plant fall into either of two categories: a bottleneck resource or a non-bottleneck resource. A bottleneck is any resource whose capacity is less or equal to the demand which is placed upon it. A non-bottleneck is any resource whose capacity is greater than the demand which is placed upon it. The key about this resource optimization technique is that The bottleneck resource will govern the throughput, and the bottleneck may not always be the same. Therefore, it is important to focus resources on the bottlenecks. Next slide, please. Now that we know some of our operations and bottlenecks or the bottlenecks, how do we identify them? Our first recommendation is to use the definition of a bottleneck. We can find out the total market demand for products going out of the plant and find out how much time each resource has to contribute towards filling that demand. If the available time is less than the demand, then we can say that the operation is a bottleneck. Now let's see how to apply this to our case. There are 4 models of aircraft. The current production rate is the completion of all sidewalls for one smaller airplane per day that has an average of 24 sidewalls. Plus, every other day the plant completes a set of sidewalls for the larger plane using an average of 28 sidewalls. The other 2 models require 42 sidewalls per plane and the shipments are made once a week. So basically, we know the production rate for the first 2 models and the market demand for the last 2 models. Unless we assume that the current production rate is equal to the demand, we don't know that demand for the first 2 models. Let's say we go ahead and make that assumption. Now, we have to look at the current capacity. Here again, we do not know how many operators are involved in each of the last 3 operations. So, again we have hit the dead end. So, what do we do now? Is there any other way to identify a bottleneck? Next slide, please. Here we have other ways to identify a bottleneck. There are 3 things we should know about a bottleneck. First, a bottleneck is a step where problems usually start. Next, a bottleneck usually has a huge work in progress inventory before it piled up. And finally, the parts most frequently in short supply are probably the ones that will pass through the bottleneck. Now let's see if we can make use of these points to identify the bottleneck in our system. First, let's look at the fact about the bonding process. Jim complains that bonding most of the time in which the order is always stuck. MRP lead time is the highest for bonding operations. Maximum daily production is 39 parts in one shift. So yes, bonding can be our bottleneck. Now let's take trim and drill operation. First, the trim and drill is that its capacity depends on the number of skilled workers. So we can't be sure whether it is a bottleneck unless we know the number of workers. But one thing we should be sure is that the maximum capacity of layup is 63 parts per day if the operation is made in 3 shifts. So if trim and drill produces less than 63 parts every day, it is a bottleneck. And for this, it should have less than 5 workers assigned to it. Then orders for drilling are delayed frequently. And finally, the largest pileup of inventory was found in front of trim and drill operation. So yes, trim and drill can also be a bottleneck. Next slide, please. And I would call upon Praveen to continue with the next slide.
Thank you, Shiva. Now we have identified the bottleneck. Now what new approach should sidewall follow? Let's look at both the scenarios. The first one is what if bonding is a bottleneck. In this case, sidewall has to first exploit bonding by running the process for 2 shifts. The maximum production capacity will then grow to 78 parts from 39. But why not run it for 3 shifts? Because when we make bonding, it produces 78 parts. The bottleneck is already moved up to layup, which currently produces only 42 parts. So we run layup for 3 shifts per day so that its capacity increases to 63 parts. Now we have bonding produce more than the layup. We don't want that to happen, and so we can stop bonding every day when 63 parts are produced. The next thing we can do is to see if the old bonding oven is still functional and has the capacity to produce 63 parts per shift along with the new one. Then we need not run an extra shift, which will reduce our operation cost a lot. Once we have decided how much time we should run each operation, we need to assign workers who are responsible full time for what happens at bonding and layup and make sure we don't move them to other processes for expending orders. We do this because an hour lost at the bottleneck is an hour lost for the total system, but an hour saved at the bottleneck is a mirage. Once we have done that, we move the inspection before bonding. The bonding step to check parts going into bonding, because if you scrap a part before it reaches the bottleneck, all you have lost is the scrapped part. But if you scrap a part after it has passed the bottleneck, you have lost the time that cannot be recovered. But what if parts become defective downstream from the bottleneck? For that, the only solution is we need a very good process controls on the bottleneck parts. If the drilling continues to have a high flaw rate, we can move inspection before drilling. Finally, and the most important of all, we can now reduce manufacturing lead time on all the processes, since the flow through the plant is now balanced with the demand after implementing all these steps. So, by little slug, we have reduced work in process inventory and increased inventory turnover. Next slide please. The next scenario is, what if trim and drill is a bottleneck? Here again, we exploit trim and drill operation by assigning 5 skilled workers for 1 shift per day to trim and drill. The production capacity will then grow to 65 parts per day in 1 shift. Once we have done that, the layup becomes the new bottleneck, and we run it for 3 shifts to increase its capacity to 63 from 42, which is the current production rate. Then we assign workers who are responsible full time for what happens at the trim and drill and layup, and make sure we don't move them to the other processes for expediting orders. But trim and drill is not an ordinary operation, and it requires highly skilled workers. So if 5 skilled workers are not available, we can subcontract trim and drill operation to a vendor with the right equipment and people. Now, since trim and drill has high flaw rate and those flaws are identified only during the assembly, we can reduce rework by moving the quality inspection after trim and drill. Finally, we can now reduce the manufacturing lead time all the processes, since the flow through the plant has now balanced. Once we have next slide please. Once we have implemented all the solutions, we can see that the manufacturing lead time can be reduced to 12 days from 100 days which was existing earlier. Since the flow of the plant is balanced with the demand, it's no longer necessary to store excess inventory between the processes. This will reduce our work in process inventory by 86% and help us achieve a 7 times increase in the inventory turnover. Now I would like to call upon Mr. Vimal to continue.
Thank you, Praveen. Look at how our solutions have helped us to address the sidewalls problem in terms of our goals. First, since the utilization of bottleneck is increased, we have increased the overall throughput of the plant. Next, since the manufacturing lead time is reduced drastically, our inventory of the plant goes down. And finally, since we are not focusing on maintaining 100% efficiency, our operating expenses will come down. So essentially, we are making more money now. Then let's take a look on the new levers. Our mode of operation has now changed from dedicating capacity based on demand on as needed basis to sticking to a new fixed plan. All orders in our plant can now be shipped on time without expediting orders, enabling us to achieve an improvement in our on-time delivery goal. And most importantly, our inventory turnover has now increased by 7 times. Another point is that the case mentions that efficiencies were preciously high, but now they are dipping again. With our approach, efficiencies will dip somewhat because the plant was consuming excess inventories. When the inventories are exhausted, which will happen as a result of increasing throughput, efficiencies will come back again. Next slide please. The final question is, what is expected output of the plant? Here we see that each of the progress is capable of producing 63 units, which is the throughput determined by our bottleneck. Looking at a model Y split, we can divide this as 30 sidewalls every day for small aircraft models and 15 every day for large aircraft model and 9 sidewalls each for other 2 models. Looking at the shipping schedules, we can ship 30 small craft sidewalls every day, 30 large aircraft sidewalls every other day and 42 sidewalls each every week for other 2 models. By this, we will be able to meet our demand and even exceed in case we get more sales. So, to summarize, we have looked at the problems faced by sidewalls, the new approach that they should follow, how the approach will successfully solve sidewalls problem, and finally the expected output of the plant. Thank you. Thank you.